Before proceeding further, let me first recapitulate what we did in the last lecture, that is on the fourth lecture on Schrodinger equation in 1D. For a symmetric finite potential well, we found that the solution decouples into two categories. The even category is this and the odd category is this. The application of the boundary condition leads to the conclusion that the bound state for even category states is governed by y even phi, which is and for odd category state it is governed by where we used u is equal to Ka and um is equal to twice mv0 by h line square times a. Sorry. This is and this is related to the strength of the potential. So the solution or the energy eigenvalues, energy values is related to K, and this is in turn related to the dimensionless quantity U. So the U for both even and odd parity states are to be solved from this transcendental equation. What we did, we first plotted the cot u function and y even. The intersection of cot u with y even gives the energy K values corresponding to even parity states, and which in turn leads to the energy values. And on the other hand, intersection of cot u with y odd gives the energy values or K values corresponding to the odd parity states. We found that the cot function is positive in the first half of each interval of pi and is negative in the second half. Y even is always positive. As y even is always positive, intersection of cot u with y even takes place in the first half of each of the interval of with pi, while the intersection of cot u with y odd takes place in the second half of each of the intervals. And the property is that at u tends to y equals to plus infinity and y o goes to 0 is the guiding factor. So the number of bound state that is obtained depends on the strength of the potential, that is on The larger the value of the larger is the number of bound states. If we consider the u0, the lowest energy levels, the first intersection takes place with cot u with y even, and it takes place at a value less than this. Then the first excited states, which come from an odd parity states, intersection takes place between pi and pi by 2. The second excited states, which is again an even state, which is an even parity states and comes within this range. Now, if we consider the how many are the bound states for a value of if is less than pi by 2, the number of bound state is 1, and if lies between pi and pi by 2, there are two bound states, because lies between there, so there will be two bound states. If lies between 3 pi by 2 to pi, there will be 3 bound states. Continuing in this fashion, if happens to lie between n into n pi by 2 to n minus 1 pi by 2, there will be exactly n bound states. So this denotes the number of bound states. For an infinite potential, well, is infinite, and that's why there were infinite number of bound states. And if we find that as increases, this intersection point approaches the pi by 2, 3 pi by 2, 5 pi by 2, etc. And on the other hand, these intersection points will approach to pi, 2 pi, 3 pi, 4 pi, etc. So in that case, the energy wave number becomes equispaced. The wave number corresponding to the energy eigenvalues becomes equispaced. But in general, if has a finite value, these k values are no more equispaced. Secondly, we talked about the wave function. In discussing wave function, I have made a wrong statement that this wave function comes from sine part, so it should be like this, not this was wrong. This is wrong. So the correct wave function corresponding to first excited state is this. This is the correct wave function corresponding to the first excited states. That's all about the recapitulation of the earlier class. Now I am passing over to the case where E greater than 0, that is the scattering case. The same problem is there, but we shall the initialization of the problem is different, and the mathematics involved will also become different from what we have done in connection with the bound state problem. So scattering case. The initialization of the problem is that a free particle, this is region 1, as usual this is region 1, a free particle of energy E approaches the well from left hand side. So the initialization is different. A particle of mass a free particle of mass mass m and energy E greater than V0 approaches the well from left in region 1. This is the initialization of the problem. Now what happens, if we write the wave function in region 1, the wave function is phi 1 double prime plus k1 square phi 1 is equal to 0, with k1 square is equal to twice m E by h line square, and it is g, and it is greater than 0. So the solution of it is This is the incident particle phi I, and this is the reflected particle. So if we consider the particle, the initialization of the problem is that the particle of mass m, free particle of mass m, which is represented by a plane wave, is approaching the well from the left in region 1. Then this is the phi I incident wave. Impinging on the well, a part will be reflected. This is not a classical phenomena. According to classical physics, since E is greater than V0, every particle will overcome the well and come to the region 3. But in quantum mechanics, we represent the particle by wave, so it will have a reflection as well from. So there is a difference between classical physics. Now in region 2, the wave function is phi 2 double prime plus k2 square phi 2 is equal to 0, where k2 square is equal to twice m E minus V0 upon H line square. Since E is greater than V0 for scattering case, K2 is a real number and that is K square is this. So the solution, this is C e to the power I K2x plus D e to the power minus I K2x. The wave that comes into the region 2 is again behaves as a free particle, and it falls on the right wall of the well, and the wave that is and it's getting reflected, a part of it being reflected from the right end and travels towards the negative x-axis. The totality of the wave that is moving in the positive x direction in region 2 is represented by this one, and this is the wave that is moving in positive x-axis, positive x direction, and this is the wave, totality of the wave that is traveling towards the negative x direction in region 2. And in region 3 we will have phi 3 double prime plus k1 square phi 3 is equal to 0, because here I have made a wrong statement here. Sorry, it is E minus V0 because the potential is, and here the potential is 0 by assumption. So, and K1 is same because the potential is V0 in region 1 as well as in region 3. The physically acceptable solution of this is f e to the power plus I k1x. There is no reflected wave in region 3 as there is no more discontinuity in the potential. Here there was a discontinuity of potential, so there was a reflected wave in region 2, but there is no reflected wave in region 3. And furthermore, I haven't used the word E so as to avoid confusion with the energy E. So altogether we have three wave function. As the calculation is lengthy, I am just collecting the relevant parts. So phi 1 is equal to A e to the power I k1x plus B e to the power minus I k1x. Phi 2 is equal to C e to the power I k2x plus D e to the power minus I k2x. Phi 3 is equal to F e to the power and the k1 square Now we have to apply the boundary conditions. These are the summary of the wave function that we have calculated. The boundary condition is phi 1 at minus a is equal to phi 2 at minus a. This gives you phi 1 this a e to the power minus I k1a plus b e to the power plus I k1a is equal to c e to the power minus I k2a plus d e to the power plus I k2a. Phi 1 prime at minus a is equal to phi 2 prime at minus a. This gives you, if we differentiate this ik1 will come, and from this will ik2 will come. So this is this minus sign is the differentiation of phi 1 brings a minus sign, and I gets cancelled. Then on the right wall we will have phi 2 at a is equal to phi 3 at a. This gives you c e to the power I k2h. Note the change in sign. Note the change in sign. Phi 3 prime at a. This gives you k2 will come out c e to the power plus I k2a minus d These are the four equations. We can solve these two equations to express C in terms of F and B in terms of F. We can write C is equal to something times F and D is equal to something times F by solving these two equations. Then if we substitute these two values in the first two equations, we get two relations. We get two relations A, B and F, and obviously there will be K1, K2 and A dependencies, which gives us, as we are here interested in the transmission coefficient, we get that F by A modular square. Before going to this, we really like to define the reflectance and transmittance. The reflectance is defined as R is defined as So you know that Ji, the incident wave, is equal to hk1 by m a modulus square x cap. This is the direction of x cap. J reflected, as we have calculated it in other classes, h line k1 by m b modulus square x cap, and transmittance in this third region. So this is the reflectance. This basically becomes b by a modulus square, and the transmittance comes out to be jt by ji f by a square. Note that in that case r plus t is not equal to 1, because there are some particles in this region too. The forward moving and the backward moving components are not the same, so there will be some particle trapped within this, which is again non-classical result. So we are interested in the transmittance for this case. So we are interested in f by a. A point to be mentioned from examination point of view, such a question was set in a few years back, and it was decided that the majority of the marks will be provided to students who can write up to this much correctly. You need not to simplify, because the calculation is very tough and it is not always possible to simplify the relations in the examination hall. So if such question arises, be careful in writing the boundary conditions correctly, and then tell the scheme how to calculate this, and it is obvious that you know the expression of t is equal to f by a whole square. Now on detailed calculation, we found that t is equal to f by a whole square. The transmittance t is equal to f by a modulus square, and this is equal to k1 square k2 square if k1 is equal to k2, the transmittance is 1, but k1 is equal to k2 means v is equal to v0 is 0, that is there is no well, so this is not a quantity which is of interest to us. If we could write this in terms of E, the result comes out to be, on simplification, I have missed square over here. One thing is that if we want to find out the variation of t with E, we see that at E is equal to 0, this part is 0. At E is equal to 0, this part is 0 and the transmittance is 0. So at t is equal to 0, transmittance is 0, and as E increases from 0, the transmittance varies in such a way. Let me first draw the graph and then I will explain it. This is a one line. It approaches these are the points at which the transmittance is the maximum. So t is equal to 1 with sine of 2k2a is equal to 0 is equal to sine of n pi. If we that is 2k2a is equal to n pi, or k2 is equal to 2 pi by lambda 2, the de Broglie wavelength within the well is equal to n pi by 2a, or you can write 2a if this condition is satisfied, then transmittance is 1. This is condition transmittance of unity transmittance. That is, the width of the well is such that there are exactly an integral number of half de Broglie wavelength within the well. If the well is such that it accommodates an integral number of half de Broglie wavelength, then the transmittance is 1. And if we have this to be 2k, and for minima which is not equal to 0, mind it, twice k2 a is equal to n plus 1 pi by 2. This represents this point. At this point, this condition is satisfied. One interesting thing is found with higher inert gases or heavier inert gases. Gases like argon, krypton, xenon, it is found that if we bombard it with electrons, then at some critical values the entire electron passes through the inert gas. That is, to this electrons of specific energy, the inert gas becomes as transparent. If we consider the inert gas, it has a spherical electronic structure and is a tight binding. So if we consider the electrons, the potential within an inert gas, which has a sharp boundary, so we can call it a spherical potential well. Spherical potential well. If we take its one-dimensional analog, then this may be a one-dimensional model for alkali atoms. And if we see that the transparency means these points, that with just amount of energy, the electron being bombarded towards the atom with just this energy, and if this condition is satisfied, these conditions of maxima are satisfied, the electron passes through the atom, and the atom appears to be transparent to the incoming electrons. If we consider what should be the energy of this electron, the energy of the electrons should be such that this condition is satisfied. For n is equal to 1, we have, for transmittance is equal to 1, we have K2 is equal to n pi upon 2a, and we go to pi by 2a with n is equal to 1, that is the prominent one, and the corresponding energy EC is given by h line square K2 square by twice m, because the definition, you recall the definition of K2 is this. So this gives you the critical energy of the electrons. So we write it as h line square twice m and pi by 2a whole square. So this is h line square pi square h line square, and this is, if electron is bombarded with exactly this energy, it passes through the heavier inert gas. For the lighter inert gas, like helium, neon, the depth of the potential is not sufficient to satisfy this condition, and so this effect is not felt. This is called Ramsauer effect. For atoms other than inert gas, they do not have a soft spherical boundary, so the theory does not work there. With this, we complete our discussion on the scattering aspect of one-dimensional finite rectangular potential well.